Okay, so I will discuss about multi-component ultracold atoms in non-abelian gauge field. So for me, multi-components mean 2 or 3. So this work, I'm affiliated in Nanyang Technological University, which is in Singapore, and University Côte d'Azur, which is in France. But the work that I will present today was done in the Center for Quantum Technology, which is located in Singapore. Maybe I should have the, what is it? This one? Okay. Yeah, so I think the key idea here that I will discuss during this talk is parallel transport. So parallel transport connects vectors in the tangent space of a manifold along a smooth curve. So that's some kind of definition. So usually people like to show as an example the Foucault pendulum, that you know that if you are not exactly at the equator, you are in some latitude, the Foucault pendulum will start to precess. And in fact, the vector, which is, for example, normal to the plane of oscillation of this Foucault pendulum, will rotate and will do a parallel transport. So with a bit of imagination, let's suppose that this is Earth, right? And the parallel transport is somehow you take a plane like that, and then you draw some parallel vector here, right? And then after that, you try to wrap this plane into your non-planar geometry here. So for example, if I wrap here on the equator, so I wrap on the geodesic, you can see that all these vectors remain parallel. So here there is no somehow rotation of the vector here. But now if I am on the, not be so easy, but if I am on the, not on the equator, not on the geodesic, then if I rotate, I will form a cone here. And what you can see here is that now the vector has some angle, okay? And this is the angle of the rotation of this Foucault pendulum. So this is the idea of parallel transport in classical physics. You can also go to the quantum regime. And in that case, there was an important contribution done by Michael Berry, where he considered a single component states here, and then he do a parallel transport, and then he find that somehow this parallel transport is characterized by a connection, like any parallel transport, and this is not what we name the Berry connection here, A, or if you prefer, the gauge field of the system here. And the Berry phase is just the integral over a contour of this Berry connection, and this is this Berry phase is gauge invariant here. So what we are interested in this talk is not only this Berry connection, but is the impact of this Berry connection or the force which is associated to this Berry connection, and this is given by a Berry curvature. So you just have to take the curl of A here, and then you have a non-conservative forces. So it's like the Coriolis forces if we are talking about the Foucault pendulum. And of course, you notice here that there is a very trivial case, is when A is homogeneous, so it doesn't depend in space, but there is no force, and then this is trivial here, or if you prefer, you can gauge away the gauge field. There is no more gauge field, no more forces, and so on and so forth. So this is the situation where you are in a U1 symmetry, so when you have only one state, and then only the phase is the free parameter, but you can go now to a more complex situation, where you have now n-degenerated multi-component system, so in our case will be 2 or 3. In that case, the Berry connection becomes a vector which has n by n operator as a component. And then if you look now to the Berry curvature, you find that there is an extra term which coming here, which is the curl of A with itself, or if you prefer, the commutator of A. And so if this do not commute, then you have a force which is here, even if A is homogeneous. So if saying in other ways that you have internal state that do not commute, so there is some dynamics, internal state dynamics here. For example, if you're in SU2, you will have rotation, and this rotation will give rise to forces. And these forces actually, in fact, there is a clear connection with spin-orbit coupling that we hear during the previous talk and another talk, spin-Hall effect. It's also similar to the Zitter-Bewegung lac effect. So Zitter-Bewegung is something which is predicted by the Dirac equation. It's a relativistic effect where you have oscillation between a particle and antiparticle here. Or you can also think about similar of a neutrino lag oscillation. So this somehow, this effect, that's what we're going to discuss today. And in addition, also, I will discuss about gate operation using this kind of geometrical transformation, where we, in fact, interested only in the internal state manipulation of the system. Okay, so this SU2 non-Abelian gauge field, we start with SU2, so 2 components, is not something new. I mean, something was done quite some time ago, and actually the first experiment along that line was done by Jan Spielmann here in the audience, where he used Raman coupling, and this is also what Sarah has showed us during the previous talk, to address, to create some spin-orbit coupling. In the lattices, there is also a Raman-assisted tunneling effect. We see also some shaking method that you can use. In my case, I will use something which is a little bit different, and that was initiated by our guest here in Vilnius. So it's a tripod scheme. So if you have a tripod scheme here like that, and then you shine it with redundant laser, you have here 2 dark states. So these dark states are linear combination of the ground state, which are decoupled to the excited state thanks to destructive interference here. And these 2 dark states will be geometrically coupled, and then you can generate this non-Abelian gauge field. It's very different from the case where you have here another system, where you have also 2 dark states in this system, but these 2 dark states are completely decoupled. So there is no non-Abelian gauge field here, but in a tripod there is. So in order to see that more clearly, you can write the Hamiltonian of the system here. So again, we have this resonant tripod here. And then you are diagonalize this interaction term here, and then you find in the dress states picture, so we'll find 2 dark states here, okay, which are not light shifted, and 2 bright states which are light shifted. You have to make a light shift which is strong enough experimentally, such that you are isolating your system into this dark state manifold here. And then you can do an abiotic evolution, so you can write down in this subsystem here the effective Hamiltonian. So we'll find this shape here, where you have here the appearance of this gauge field structure here, and that's the component here of this gauge field. You have also a scalar field, which is not very important in our case. So non-Abelian, okay, it means that I just repeat this for the sake of clarification. It means that the component of the vector A here, which are operator, do not commute. And if you have n dark states, then you will have, and the underlying symmetry will be SUN here. Okay, so we have the Hamiltonian. We can derive the force using the Heisenberg picture. So we can write the force as the derivative of the velocity. The velocity is shown here. And then you find the force has this non-conservative like structure here. Now, of course, the force is non-zero only if the 2 operators, if at least 2 components, of A do not commute here, and is also perpendicular to the momentum of the system here. Okay, so how we do that in practical in the lab? So we use strontium-87 atom, and then we are doing a sequences of cooling, so laser cooling on the broad transition, on narrow transition. Then we do optical pumping and evaporative cooling. And at the end, we have degenerate Fermi gases, where the degeneracy is given here. Actually, the fact that the gas is degenerated is not very important for us, because it's just single particle physics that I will discuss about today. But what is important is that we are in the subrical temperature regime here. Then when we have done this, we turn on our laser beam that do this non-Abelian gauge field, this tripod beam. Then we wait for some times. And then after that, we do a time of flight. And then we look what are the momentum distribution or the velocity distribution into this system. And what is interesting here is that these 3 beams that we use for the tripod have this orientation which is shown here. So initially, we start in the state 3 here. And then if you go, for example, to the state 1, you have to absorb 1 photon here and emit 1 photon there. So you will have a 2 h bar k change in momentum. And then so you will find a distribution which is shift by 2 h bar k, which is this distribution here. So you identify this distribution to 1. Then if you go to the state 2, you have a similar mechanism between 3 and 2, and so you identify this distribution as a set 2, and the initial one was a set 3. So you can, looking to the momentum distribution, you can also come back to the internal dynamics of the system. So here in this slide, so we create a non-zero momentum, and again, so we have a non-Abelian gauge field here. So the system is completely stationary, and what we observe some oscillation here of the system. So this oscillation is just an oscillation between the two eigenstates of the system, and these two eigenstates have different velocity here, and so we see this oscillation in velocity, and that's similar to this Zitter-Birigun effect predicted in the Dirac equation. It's also similar to a spin Hall effect, because if you look again to this formulation of the force, you find that the force and the momentum of the particle are orthogonal, as you expect for a spin Hall effect. And that's what we show on this graph here, where we plot here as a function of the angle, of the boost angle, so of the momentum that we give to the atoms, what will be the angle of these forces here, this oscillation, and with respect to the boost angle here, and then you find that you can be always at 90 degrees, so 0.5 or minus 0.5 here. We also extend this problem to SU3 more recently, so it's a bit more complicated to do, but basically we do 2 tripods like that, and then if we diagonalize this system, you find, so you have 7 states here, 3 states are dark, and 4 states are bright here. And then we just start initially with a cloud which is here, located in these states here, and then we look how this system evolves. And so what is the difference between a SU2 system and a SU3 system? In the SU2 system, there is only 2 states, or there's only one characteristic frequency of the dynamic, whereas in SU3 you have 3 states, so you have 3 different frequencies. And these 3 different frequencies are here. So this is the Fourier transform of the dynamics here. So they are shown in the dashed line here, and you can see that according to which population you are looking, you will find experimentally the frequency here. Okay, so what we use also, this tripod, is to create some stirrup, which is a little bit special. So usually a stirrup, you have a lambda system, and then you transfer the spin to one, or you transfer the population to one state to another state, right? So you do some kind of complete transfer of the spin. If you have a tripod, and this was also proposed by the group in Vilnius here, you can have a knob somehow to control the orientation of the spin at the end. And this knob, it will be one of these beams here, and it's basically the beam that controls the initial population of the spin here. So we perform this experiment, and so we don't launch the atoms, but we just turn on and turn off the beam, following this kind of Gaussian distribution here. And what we observe is somehow summarized into this cartoon, where C, what is important is that C, in fact, is proportional to the Rabi frequency here, the peak Rabi frequency of the beam tree, which is this one at the center, and that's where the initial population is. So if this beam is completely off, you stay where you are here, and then if you start to increase this Rabi frequency with respect to the other 2, which are equal, then you transfer, you can control somehow in a geometric manner the orientation of your spin here after these 3 pulses here. Okay, so we have here a way to for example, to do Hadamard gate here, and then what we are interested also to say, can we do some kind of geometric Ramsey interferometer with this kind of system? So we start with 3 pulses here. Okay, so that's what's happening somehow in time. So we start with 3 pulses. Everybody is in 3 at the beginning. Then after the 3 first pulse, we create a coherent superposition between 3 and 1 state here. And then we turn on the pulse with another, in another way. So actually the final one becomes the first one, the second remains the second, and the first one become the last one, and then we transfer the population now into the state 2 here. So you have some oscillation into the system, because if you are in between here, you are in a superposition in 1 and 3, which doesn't have the same momentum. So you have a frequency, which is given by this momentum difference here, which is 2h bar k in our case here. So the frequency will be something like that. So you can see this oscillation is extremely, very rapidly dumped, because the coherence time actually is quite short in our experiment. It's only 23 microseconds because of the finite temperature of the gas, so we are not very, very cold here. Okay, so this is somehow a way to construct a gate. You can also use SU3 to construct the gates here. So what we do now is that we, in this cartoon here, we create some Hamiltonian where we change some phases of all those lasers in order, for example, to connect the state in red here to the state in green. And then what you see as a function of time, that initially we are here, and then we are transferring the population into this, to the other state. We can also use another set of phase and amplitude that we vary, and then we now connected the state red to the state green, but via the state blue here. Okay, so that's also very important properties of SU3 symmetry. So what is the difference between SU3 and a spin 1 is that in an SU3, all the sets are connected all together. Okay, so that's what you can see into this cartoon here. You can also say, oh, let's try to use this to generate some gate. So you can have a SU2 NMR gate here, you can have a SU3 NMR gate here, but it's not fantastic. Somehow the fidelity is not that great, simply because the system is way too complicated. We have too many lasers, too many uncontrolled transitions that make the fidelity poor. So how we can address this system? We go back to somehow to just we come back to the tripod scheme here, and then we authorize somehow eventually some population into the excited state. As far as this population is not big, and then we can do the gate rapidly enough, there should not be a problem to have a high fidelity gate. And in order to address this problem, we use the optimal control approach, which consists of minimizing a cost function, which is shown here. And this cost function has two quantities. The first quantity is the fidelity of the gate. So the infidelity of the gate, sorry. So you want this infidelity to be as small as possible. And you want also the excited state population as well to be as small as possible. Okay, so we let the system run, and then the system gives us this plane curve. So what you see in black is the phase of one of the lasers. Actually, it's enough to address one phase of the laser. And the rest here are the amplitude of the laser here. So we do this in the experiment. In the experiment, it's not perfect. We do the dash line here, but it's not so bad. And that's what we observe. So we do a full tomography of the Hadamard gate. So this is what I represent here is the Shaw matrices of this Hadamard gate. So that's what we expect ideally. That's what we expect when we do the simulation, and that's the experiment. Okay? So in terms of fidelity, so what you can see is that the optimal control gives an excellent fidelity. The simulation is also very good. The experiment is not that great. And in fact, it's mainly come again to the fact that there is some temperature, and at some point the gate still, even if it's short, still remains finite in time. So the wave function move a little bit here, and that reduce the fidelity. Everything is done in free fall here. Okay, so how we can improve somehow the coherence into the system? We know that in order to improve the coherence, we can do a hand echo type of experiment. So basically, you know, if you have a SU2, so you are in the North Pole, and then you go to equatorial plane, then you start to rotate in the equatorial plane. This rotation is not the same for each atom. There's an inhomogeneity energy fluctuation, and then you do an echo, so you flip one time, and then everything will be resynchronized after the same time. So if you do this in SU2 system, it's a little bit more complicated because somehow you need to have two mirror operators. So let me explain this. So you imagine that you start in the green state here. So you have an Hadamard gate, you create all the color here, and then after, since they have different momentum, they start to spread. Okay, here. And then when you are here, so here, this one was blue, and then you do a swap gate here that transforms the blue to red, the red to green, and the green to blue here. But you have to do another time this transformation in order that you can see that on each pass, you will explore all the states, all the spin orientation, in order to rephase the whole system at the end here. So if you look now how the coherence is improved here, so if you don't do this echo, so here it's consisting of these two X poly gates, you will have a rapid decay here of the contrast, and then you can improve the contrast here by 1 order of magnitude doing this kind of manipulation here. Okay, so this is a summary of the work that I present today. So basically, I would like maybe to show the hero of the story. So this is the 3 PhD students. So the first one was Mehdi Hassan, who has done the Fermi degeneracy and has observed this Zitter-Bewegung lac effect here. And then Chetan Madasu, who has, I think one of the main contributions is to have created this SU3 system and check the dynamics and this three frequency dynamics into this system. More recently, Chirantan Mitra has done this SU3 gate with optimal control here. Other group members, so this is some postdoc, Konchanchi, which is leading this part of the group, and some collaboration, which is shown here. Okay, I would like also to finish, since I have another couple of minutes, I would like also to say that it's not my only activity in my group, so we don't do only quantum simulation using non-abelian gauge field, but we have also a project on quantum sensing here. So on this project of quantum sensing, we are using also strontium, and what we want to do is that we want to build up an interferometer directly on the clock transition. So it's not only one state, but it will be 2 states that go into this interferometer. And the idea here is that, do you see any dephasing between these 2 states in the interferometer, which can be a signature, for example, of general relativity or something like that. So that's this activity here. And more recently, actually last year, like everybody in the world, so Singapore wants to put a lot of money in quantum processor. And so there was a new project that I'm leading about creating analog and digital quantum simulation. So it's not as original as we heard this morning. So it's just a tweezered system array where we have some objective in terms of fidelity and so on and so forth. So we have here a sketch with different zones that we are building now. And so we are recruiting also a postdoc and PhD student on that project. With that, I think I'm done. Thank you.
Thank you very much, David. Questions?
Yeah, very nice. I really like the geometric schemes and the tripod schemes. Would there be some extensions to realize 2-qubit gates using some kind of variant of the tripods, maybe either collisional or Rydberg or so? Like having 2 atoms somehow and then doing this? I don't know.
Yes, it's probably possible.
Yeah.
It's difficult.
Yeah.
We didn't try.
Okay.
It's difficult because I mean, you are dealing with resonant laser, you know. So if you have a collision and resonant laser at the same time, I'm afraid that you will have a lot of decoherence. So I'm not sure it's a good technique. If you are off of resonance, I mean that's what we heard. I mean, with the previous talk, I think that this is indeed possible. At resonance, it's maybe challenging. Okay. Yeah. We didn't try at least.
Yeah.
Oh, I have a short question.
Yes.
What is Q3 Hadamard? Because Hadamard I only know for. So you showed us the Choi matrix.
Yes,
I
sorry.
don't know what is the operation. What is it supposed to? Oh,
Is this? So this is the unitary operation that we are talking about.
I see, and it makes this superposition. I see.
Yeah.
Okay. So, thanks. More questions. So I will continue. You have the dark submanifold that
Yes.
you can now do parallel transport, and it becomes non-abelian.
Yes.
Can you show braiding, like demonstration of the Young-Buxter relations for such excitations or
Yes.
things like that?
It's possible, I guess. We didn't do that yet. Yes, but I think it's a very interesting. Idea indeed. Yes.
Okay.
Yeah.
I'll just keep going. Often these geometric gates have some kind of robustness associated to them.
Yes.
Do you know mathematically, or just conceptually, what are the processes that this tripod or the stirrup or these kind of things are robust against? What are the terms?
Yes.
Yeah.
Yes. So I think here the robustness comes from the adiabaticity.
Yeah.
Right. That's it. There is no topology behind this. I'm not talking about topology at all. So there is no topology here. It's just the fact that it's adiabatic, so it may be less sensitive to intensity variation, these kind of things. I don't think it's a main advantage in some way. It will be more interesting to have topology inside, of course. Me too.
So let's thank all of the speakers of today as well as David here.